Hi, this is Mrs. Valletta. I thought I would go over the fourth problem in the dynamics packet with you just to help you, because this is a very important problem to understand that tension, which provides centripetal force for many objects, is not the same everywhere, especially if you compare an object that is going in a horizontal position with an object that's going in a vertical position. So in the problem, we have a half-kilogram mass being swung in two circles with a radius of 0.2 meters, and it's rotating 2 times every second. So the period of rotation is 1 revolution for a half a second, and remember, that's tau. That's the time for 1 revolution. And if we're looking at lab group A, and they're going in a horizontal circle, every place in the circle, the tension is what's providing the centripetal force, and so it never varies. So if we want to calculate the tension is equal to mass times the velocity squared over r. So what would that be? Well, we would take the circumference, right? So it's 2 times pi r, the circumference, divided by the period in order to come up with our velocity. So 2 times pi times 0.2 divided by 0.5. So we get a velocity of we could carry a couple of decimals, 2.5, but I've rounded up. Okay, and that's meters per second. And since we said that it never varies, then the tension is equal to the centripetal force, which is 0.5 kilograms times 2.5 meters per second squared divided by 0.2 meters, and you get 0.5 times 2.5 squared divided by 0.2, 15.625 newtons. And that is the tension in the string for lab group A, and it doesn't vary, so we're going to go ahead and graph that. It's going to be up here, and they've asked us to graph it in a solid line. Not a very good solid line. I could use a ruler, but there's lab group A's data. There's A. Okay. But for lab group B is going vertically, and in each position of the circle, the tension's actually varying because in the y direction, both at the top and the bottom, weight is having an effect on the tension. So at the bottom, the sum of the forces, which is equal to centripetal force, is really tension minus the weight of the object. And if you're solving for tension, because that's what we're supposed to calculate, then tension is equal to the centripetal force plus the weight of the object. As opposed to the top, well, the top, the sum of the forces is equal to centripetal force, and we have 2 forces, and they're pointing in the same direction, and so it's tension plus the weight is equal to centripetal force. And if you want to know tension, then that's equal to centripetal force plus the weight. All right? Sorry, minus the weight. So they're different. So at the top, so for lab group B at the top, well, tension is equal to, we don't have to recalculate centripetal force because it's the same mass with the same circumference and the same period. So we know that centripetal force is 15.62, and we need to add the weight, and that's 0.5 kilograms times 10 meters per second squared, so that's 5 newtons. So at the top, our tension is 20.62 newtons, right? When we get to the side, well, at position number 2, it should be identical to what it was when we had the horizontal position. So this is position 1. At position 2, it should drop back down to 15.62 newtons. Okay, at the top, position number 3, instead of adding the weight, we said that we would subtract the weight. So that would be 15.62 newtons minus 5 newtons. So that would give us a total of 10.62 newtons. And finally, in position number 4, we're back to just tension again. There are no other forces causing centripetal motion, and that's 15.62 newtons. So for every cycle, we have 4 tensions that we have to deal with for lab group B's object. And you got to think about the fact that it's rotating every 0.5 seconds. So whenever it gets to the same position, it's 1 second later. So just for simplicity, we're going to start in position number 1. And in position number 1, we have a tension of 15.62. All right, so I'll go over here, and my tension, 20.62. That's at the top. So we're starting up here at 1/4 of our rotation later. We're down at 15.62. So 0.5 divided by 4. So that means every 0.125 seconds. So it's going to be approximate. So at 0.125 seconds, so about 1/4 of the space, we're here. It drops all the way down to 10.62. We're right about there. We come back up to 15.62 and all the way back up when we get to the end of the cycle. All right, that's going to look like this, and I'm going to repeat the pattern for every half a second. Okay, and there you have it. You've graphed the tension. It did say a dashed line. I did forget to do that, but that's okay. We're color coded, so you'll be able to tell the group. And this is lab group B. Hopefully that helped you understand the difference in tensions at different positions of the circle. Thanks, and look forward to seeing you in class.